You can stay up to date with our information on the SEI Philly website, as well as get your PDHs from the SEI Philadelphia website. Today, at the end of the meeting, I will put a link within the chat for everyone to go to and get your PDHs for download. So meet the board. This is our SEI board for this year. Everybody does their part and works hard on different aspects of SEI. Right now, we have had our most concerted effort with the golf outing that we'll actually be having tomorrow, and some of you on the call actually might be attending. I'd like to thank Nikki Mike Urban, and Colin Drager, especially for charging ahead and leading that. So see everybody out there tomorrow on the 19th at Kimberton. So golf outing sponsorship. These are the sponsors from last year. This will get updated for the sponsors that we have for tomorrow's outing in the upcoming year. So most of these sponsors are repeat sponsors too. So thank you to them. And overall, welcome to today's presentation, May 18th. Please mute yourself when you're not speaking, and questions will be addressed at the end. Please just type questions into the chat window throughout the presentation. And at the end of the presentation, we'll have about 5 to 10 minutes in order to answer those questions. And I'll moderate the different questions that we have within the chat to the speakers that we have here today. So for the topic at hand, it is the CSVT Bridge Design and Construction Challenges. So this is a local project that had a lot of excitement around it, and that's why we have a lot of individuals that were excited to listen to this presentation today. So I'd like to introduce the presenters. We have Jason DeFlitch. He is the contractor service manager at SEI Consulting Engineers. He oversees alternate delivery and construction engineering. He's a graduate of Penn State and a registered professional engineer in 6 different states. So he's presented various papers at the IBC, as well as worked on a multitude of different bridge projects, and lives in North Huntington, PA, with his wife and 2 daughters. Next, we have Matt Stahl from Trumbull. He's a project engineer at Trumbull and received his BS from University of Pittsburgh and is a PE in Pennsylvania. So sorry, Matt, should have put your PE here. Over the past 14 years, Matt has overseen various construction projects, including CSVT, and he's currently working on the southern section of CSVT. And then last but not least is Ahmad Ahmadi, the chief bridge engineer at SAI Consulting Engineers. He received his BS from University of Shiraz, Iran, and his MS and PhD from University of Pittsburgh. Ahmad is a registered PE in 7 states and has been with SAI since 1986. So welcome to the 3 of these individuals, Jason, Matt, Ahmad. I will hand it over to you, and I will stop presenting.
See my screen, Jack?
Yep, can see it good.
Okay. All right, thanks everybody. I'd imagine most people here know of the CSVT project, but start off by giving a quick overview here. It's the Central Susquehanna Valley Transportation Project. It's located where you see the yellow star on the screen there, just south of I-80 in central Pennsylvania, right along the SR-15 corridor. That corridor runs all the way from Harrisburg to I-80, so you have a lot of through traffic there running through that corridor, but a lot of small towns and a lot of traffic generators there, a lot of left-hand turns. So this project would help get folks around there, improve traffic flow and safety along this corridor. There you can see the different sections that are involved in the project. So the northern section that's built, the central portion of the page along the west branch of the Susquehanna River, that's where our bridge is right here. Northern section being open, and then as Jack mentioned before with Matt, he's up there now building the southern section, which will connect everything down in through Selinsgrove. This will get folks around that busy area of SR-15, get across the river, and then make connections to points north to I-80. Just a quick look at the topography of the area that we're talking about here. You can see the spur coming out in the middle of the screen there, right in the west branch of the river. That's where our structure is going to be. Kind of goes over some low-lying areas, a little bit of adjacent residential areas, over these islands that you see in the central portion of the screen. And then eventually does get into the railroads on the far side, and then connecting up through to points north. So if you want, there is a website, csvt.com. You can check out. They still have updates up there for the ongoing project, southern section right now. The purpose, as I mentioned before, was to kind of get the trucks and the through traffic away from the local traffic to improve safety and then traffic flow as well. So to do that, we're going to build a new 4-lane structure there, limited access highway through this area. It ends up being roughly 13 miles long, and it's separated into 2 sections that we saw on the couple slides before this. So we'll go through some of the challenges here with the bid phase, design phase, and then get into construction. I'll talk about the superstructure. I'll talk about the substructure and mat and the construction end. Real quick on the big phase before we move in, this was an alternate design. It was listed, plans were posted before advertisement as a planned project, and reviewed by a contractor with SEI and Trumbull together. Planned for this advertisement to come up with a essentially alternate superstructure and some substructure adjustments. That was then advertised and let in September of 2015. TS&L was finished by the end of 2015 in December, and then the substructure design was submitted in March of 2016, and superstructure thereafter in April. So it was a very tight schedule, being an alternate design to try to keep everything on track with the original design schedule that was planned. So starting off with the first design topic is the superstructure. Going to talk about a general overview of the superstructure design, get into the 3D modeling that was required, how that tied in with the girder design, and then some of the secondary members of the diaphragms, lateral bracing, and then touch on the deck a little bit. So here's a general overview of the whole structure. As you can see, the total length of 4,545 feet, so nearly a mile-long structure. Was split into 15 spans, 3 units each, with each unit being 1,515 feet. This is all per the original design. None of the pier locations were changed to maintain all the permitting work and the H&H work that had done on the project. So the focus here was to change a little bit on the superstructure and hold those pier locations, and then assess the piers. So you can see the span range from 238 feet, 350 feet. Most of the units, Unit 1 and Unit 2, have identical span arrangement, with Unit 3 some adjustment spans to get up toward abutment 2. There is where we have the 238-foot span. It was in PennDOT District 3 and roughly a $156 million contract. So what you see on the screen is a typical section of the bridge, and this is the future section. So you're seeing 3 lanes here versus the 4 lanes that I mentioned before. That is accommodated by the just over 5-foot overhang that you see on the screen. In the current condition, it would be built to just over 2 feet and then widened 3 feet to either side. That would accommodate this future typical section and allow for traffic to flow during a redecking operation. So you see the 8 girder section that we have here, the diaphragms connecting them together, and the configuration and the future condition with the 3 lanes and the 6-foot outside shoulders. So take a look at the redecking that would need to be occurred. This had to be accounted for in all design elements. So in the girder design, diaphragms as well, all the way down through the substructure. Maintaining those 4 lanes of traffic in each particular phase. So you see the first phase at the top there showing 4 lanes of traffic being maintained on the left side while we rebuild and widen to the right. Again, switch traffic over to that side that we just built, then do the left. And then of course, with longer span structures like this in particular, and the traffic that needed to be maintained, there's a closure pour between girders 4 and 5 anticipated in this redecking condition. And that each of these phases and the differential deflections, et cetera, would have to be accounted for in the design of the structure. 3D modeling, we used 2 programs to do our 3D modeling. Load 3D was a SEI program that is approved by PennDOT. We use this for live load distribution factor verification, along with the redecking analysis for the girders and the camber. And STAAD was utilized a lot for the lateral wind analysis, overhang bracket analysis, diaphragms, etc. So getting into the load 3D live load modeling that we completed on the project, we did look at 3D distribution factors, what would be an equivalent distribution factor for these girders based on a 3D analysis. We're able to combine those load effects or compare those load effects with align girder distribution factors and determine between the two, whether it was a line girder or the 3D, which one had governed, and use the worst case results for the design. For the most part, line girder distribution factors did govern, except for shears at the ends. We're able to then get this into the SDLRFD program and still use PennDOT's standard SDLRFD program for the girder analysis. Future redecking was very similar. You could 3D analysis, check out what we thought distribution factors were governing in that condition, and then account for that condition in our girder design. We did model all the diaphragms and the lateral bracing in Load 3D, and we're able to extract some of those results for the design of those numbers as well. Looking at camber, so we're able to extract camber effects for the whole deck pore sequence, taking a look at each of the pores that you see there over this long structure. This is just showing span one right now and the incremental effects of the loads per each deck pore that would affect span one. We're able to superimpose all these and then compile them to come up with a comparison of each of the girders. Once the concrete was poured in a particular span or location, we used 70% of the modulus elasticity per design manual for that concrete, and then compared each of the girder results in the end, and we're able to determine that the camber for each of the girders was roughly equivalent to each other and come up with one camber table that would be considered on the project. Further with the 3D modeling, now using STAAD, we're able to use STAAD for the wind analysis. So that's going to be governed by PennDOT VD 620, especially in that fully erected steel condition prior to deck replacement that we're showing on the screen there. So you have all the girders in place, no deck. Still need to allow for that 115-mile-an-hour wind speed that we see there. You can see the lateral bracing also modeled, top flange lateral bracing in the diagram, and then also account for the final condition wind when we have the deck in place at 80-mile-per-hour wind speed per the contract specifications, and utilize the effects for this wind analysis in our design. Girder design, you can see just one small section of what would have been a number of sheets to make up one girder within our girder plan. I can see the transfer stiffeners in there, so it is stiffened around the pier. You'd imagine over the length of a structure like this, you want to take advantage of every bit that you can to reduce section, but you also want to create some repeatability in there that creates some efficiency and economic value into your fabrication and procurement of steel for the fabricator as well. So looking at the overall girder design, the web size is 114-inch by 13/16. That was set by a span to depth ratio. That's at the depth. Once we have the depth, we wanted to ensure that we would not need a longitudinal stiffener. So we're able to take a look at our ratios there and determine what thickness of that particular web size would be required in order to prevent that longitudinal stiffener. That's how we came up with that web size and held that web size. So you can see the variation in the flanges as well, from 20/1 to 34/3 1/4. So a large variation there, but also as we're going through the design here, we want to create some repeatability of those flange sizes so that we can procure certain amounts of flange size material, cut that, and utilize that throughout the length of the girder in our transitions. It was a hybrid girder, so weathering steel 50W, 70W there. So along with the girder specifications you see below that we designed. SDLRFD, as I mentioned before, was utilized. So after we're able to make that comparison between the 3D distribution factors and the line girder distribution factors, come up with the controlling distribution factors and put them into the user-defined distribution factor command within STLRFD to account for them appropriately. Lateral stress, we could extract that from each of the 3D models that we saw before, account for the fact that we have diaphragms in there along with the top flange lateral bracing, see how that affects the stress on the girders, utilize the LAS command rather than what would be a more conservative assessment of when in STLRFD design our girder in STLRFD. We did check each of those conditions. So you have the fully erected steel, then you have the deck placement when during the actual deck placement operations, and then the final condition where the deck is hardened and we now have our composite section. So to get that economy of scale, that repeatability that I mentioned before, you have 8 girders over 15 spans. So yes, if you make small changes, those results can result in significant savings over the length of the structure itself. But you do want to create some repeatability in there for the fabricator in their procurement of steel and in the fabrication process. In addition here, the code's going to say that we cannot have an exterior girder. The exterior girder has to be at least as strong as the interior girder, but it does allow for you to have the exterior girder to be stronger than the interior girder. In this case, the exterior girder design governed, and we did make the exterior girder stronger than the interior. The web, as you see there, was as we mentioned before, set based on the span to depth ratio. Try to ensure that we weren't going to need longitudinal stiffeners, and the transverse stiffeners that you saw in the girder sheet that we showed before, that was just around the piers. Try to limit the amount of that expensive steel detailing to just where it's needed around the piers. So for the flanges, we did have a combination of grade 50 and grade 70 to utilize. Tried to have our typical rule of thumb to save 1,000 pounds of steel in order to make a transition. That tighter diaphragm spacing, of course, you want to limit the amount of diaphragms you're going to have, the expensive detailing for those diaphragms throughout the length of this structure. But you also want to gain effectiveness for those flanges. So the tighter diaphragm spacing was held just around the piers to try to help the flanges with lateral torsional buckling. And the 3D models that we had in there included the bracing loads to reduce the loads on the girder, try to maximize what we could get out of those flanges rather than a more conservative approach in allowing the STLRFD to calculate the win. So to take a look at that lateral torsional buckling, you see the sections of AASHTO that we have there for non-prismatic sections discretely braced around the pier. There's a couple of items in that section of AASHTO, which if you utilize those can help with your design. So if you extend the thicker section at least 80% of a diaphragm space, and then you transition down your thinner flanges at least 50% of your thicker flange, you can gain the maximum capacity of that flange. And something that STLRFD really isn't going to point out to you if you're at 79% that you're inefficiently using the sections that you have. So it's good to be aware of little points of the code like that can assist you in getting the maximum amount of value of the steel that you're providing in your design. Long structure like this, going to have a lot of field splices to make those to make the girder put together. So we had 384 field splices total. Want to gain efficiency out of our splices as well. We're able to use a Class B slip surface. And then in order to help out the contractor, as you imagine, it's not just the thickness of the steel plates that's going to occur here or even the number of bolts, but each one of those bolts takes a labor time and to put the girder together. The contractor in this case was looking to use cranes to utilize to make these connections in the air. So every bolt that can be saved is going to gain efficiency in the end with the contractor. It's one advantage to being on a team with the contractor that you can discuss that with them and then adjust your design to try to help out what will actually occur in the field. So we use the 1-inch bolts, minimize the number of bolts used in each of these field splices, and then try to group the splices together as much as we can. Again, trying to gain efficiency in the splice design, but gain some repeatability for fabrication and for the contractor as well. So detailing wise, all the stiffeners and splices occur at the same location for all girders. So again, creating that repeatability for the contractor and the fabricator. You saw the flange width in the previous slide that we went from 20-inch flange width to 34-inch flange width. So those transitions did occur at the field splices, which gained some efficiency in those transitions. The camber table was the same for all girders. We were able to make that comparison based on the 3D camber table that we were able to extract. And then that communication with the fabricator and the contractor really helped throughout the design to implement things such as the 1-inch bolts that we were able to utilize in the splices. So looking at the diaphragm design, again, number of diaphragms utilized throughout the length of the girder, not all that unsimilar from the splices. Want to create some groups of these diaphragms for repeatability through the structure, but at the same time want to gain some efficiency in our design. We ended up with 9 diaphragm types throughout the structure, but even with those 9 diaphragm types, we were able to limit the angle sizes used on the project to 5 different angle sizes and allow those to be reused in different configurations and in different diaphragms based on that design. So utilizing the 0.65 area reduction for single angle connection eccentricities, the DM4, that'll help limit the amount of load that's drawn into the diaphragm for the diaphragm design, and then account for the diaphragm design with each of the conditions that it would be under. So you have the final condition and the redecking condition that's going to be governed by strength 1, strength 2. But then you have your lateral forces, particularly the wind on a tall structure like this. We're going to check strength 3. That's going to be the erected steel, deck pour condition, redecking, and final conditions as well, just to verify for those lateral forces. And then fatigue as well. You have the end welds of these single angle connections made in the based on the BC 754. And that did control some of our locations here for how we detailed the size of these angles to make them. In addition to the applied load effects that we got from the 3D analysis and accounted for in the diaphragm design, diaphragm also, as we mentioned before, for lateral torsional buckling, is going to provide bracing to the girders. So you can use the criteria that you see on the screen, calculate the force that you'd expect in the diaphragms to provide that bracing support to each of those girders. It becomes an additive effect on the applied loads to the structure that then be combined in each of the combinations that we saw before. It's gonna help with you have the deck cured in the final composite condition. You'd be concerned with the bottom flange bracing that would occur in that state. And before that, when you don't have the deck in place and you're checking those conditions that you have a non-composite girder, you're going to account for the bracing force of both the top flange and the bottom flange, just minimizing when you're considering this bracing force to maximize the efficiency of your design. Lateral bracing was provided per PennDOT BD 620. That's accounted for that 115 mile-an-hour wind speed that we mentioned before, and the L over 150 limitation for deflection. So you can see for the 350-foot span that we had on the structure, the 28 inches that it was limited to before. So we centered this around the pier and incrementally worked out until we were able to limit the deflections and supply lateral bracing where it was needed. The top flange lateral bracing was utilized with a bolted connection to the top flange. We tried to limit the amount of sections that were utilized, so I used a WT8 and a WT 10.5 as the 2 different sizes for WTs that were utilized as the lateral bracing, try to increase that repeatability and some efficiency of the use of these shapes throughout the project. We included dead, live, and wind loading in these designs as well. Just one slide here on the deck design. It was the standard deck design per BD 601. However, we talked before about the number of deck pours that we have here and wanted to, with our 3D analysis, to try to do what we can to limit any deck cracking that would occur. So we're able to take a look at, through each deck pour, what the stress or what the tension in the deck would be. Take a look at the modulus of rupture to determine what strength of concrete that we would need in order to try to ensure against any cracking that would occur due to that deck tension. And it will put a table here that you see, a sample table on the plans to try to ensure against that deck cracking and limit those concerns. With that, I'll turn it over to Ahmad here, and he can discuss the substructures.
Good afternoon, everybody, and thank you for joining our presentation on CSVT bridge. What I will cover here, that is the substructure. First, we will go over an overview of the substructures, and then we will talk about design and analysis, which will consist of the nonlinear and the system analysis and the start and time modeling. And then at the end, few conclusion of the lesson we learned during this process of the substructure design. This next, Jason, please, next. Overall, there are the two stub abutment on piles, steel piles, and there are 14 piers. Those 14 piers, 6 of them, in the water. They are, 5 of those 6 in the water. They are on caissons, 8 caissons, a 5-foot diameter caissons, and the rest of them, they are on spread footing. There are 4 expansion dams on this bridge. 2 of them are finger, or the 2 dams, and 2 of them are modular dam. Modular dam are located at the Pier 5 at Pier 10. Those 2 dams displacement are approximately 22 inches displacement. On an overview of the pier cap. Pier cap is approximately 90 plus feet long and 18 feet depth. At the stem is about 18 feet. At the tip of the cantilever is about 9 feet deep. And the thickness of the cap is 9.5 foot. The stems of these piers varies from 56 foot to 159. This is from the bottom of the cap to the top of the footing. And the width of it is 28, and the thickness of the stem is 9 foot. There are some of these piers, the one in the water, is 6 in the water. There is a mass concrete underneath of them, is a plinth. The reason for those plinths is that because this structure is approximately about 60 some degree with the stream. In order to make a 90-degree structure, and therefore a plinth was constructed at the bottom of the stem, and then a stem was skewed with an angle of approximately 64 degree to the plinth to make the structure 90-degree structure. And then the footing, as I said, that some of them are spread footing on rock, 10 foot thick, and some of them are on 8 caisson of 5 foot diameter. Next, please. For the analysis of this substructures, the program we use is PA-PIR, StatPro, LPIL, SciSap, SP column, and ABL-RFT. And these substructures are designed for and analyzed for the future redecking or the final structure. The SciSap, we used it because as per AASHTO and design manual 4, approximately you have to design a substructure for 30% of the total dead load for the seismic analysis. We used the SciSap, and that resulted approximately about 10% of the total load. There was a big load reduction for the seismic in that case, and seismic did not control. For the structure analysis, that when we do the pier analysis, when you have multi-fixed pier, which in this case we had, there are 3 units. Each unit had 4 fixed pier, except unit 3, which had 3 fixed piers. When you have multi-piers, you have to do a more accurate analysis, and instead of when you have 1 pier, fixed pier, you can just take the tributary wind load and apply it, and then that's all it is. When you have multi-fixed pier, the stiffness of the system makes a difference. Therefore, you have to do a system analysis. The system analysis is when you model all your piers and your superstructure as a stick model, not complex, a stick model all together, and displacement and stiffness of each one effect. For example, in these structures, in unit 1, we have 4 pier. Out of this 4 pier number 1 attracted it in the final design, attracted it at 50% of the total horizontal loads. While if you do a simple analysis, you give it tributary 25% of the horizontal loads. But the system analysis showed that 50% of the load went to just 1 pier, and the other 50% to the next 3 piers. Besides, and as a part of this system analysis, we do the P delta analysis. P delta analysis is just simple, that all the horizontal loads apply to the structure and the vertical load. And because of those horizontal load, the structure displace, and then the vertical load act on that displacement and cause a moment. And this is a process till it's balance itself. And that is additional moment. Versus that if you use pier or V-bend, you can use the simple, those amplification factor, moment amplification factor. But per H2, if a structure, kilobar of a structure is more than 100, then you have to use a P delta analysis. And as a part of this analysis we did, it's the nonlinear analysis. The nonlinear analysis is that because how much of those total horizontal loads to apply to your system goes to which pier is a function of a stiffness of the pier. A stiffness of the pier is a function of its length and its moment of inertia. Okay, the length of your piers is obvious, you know that number. But what is I? There are different things that design manual foretells you apply consider 1/3 of stiffness for thermal analysis. But those horizontal loads is not just thermal analysis. It is a thermal, is live load breaking force and the wind force. And H2 has its own equation for I effective. But the most accurate way of computing this is something called moment curvature. Moment curvature, that's the method we use it for the stiffness computation of the pier on this for this bridge. And that is, computation of the I based on the moment. How much moment at which location of the pier that would determine the stiffness of your pier. We divided piers in 4 sections. And because, at the top you have less moment, at the bottom you have more moment, therefore, the moment of inertia of the bottom is different than moment of inertia of the top. This is an iterative procedure. We created graphs with the moment and on one column, and then on the other axis is the I of that section. And it's iterative procedure, you can imagine that for how many load cases you have, what load combination you have, it is very, very cumbersome and time-consuming procedure. However, but it is very accurate and result in a lot of saving of the rebars. Next one, please. Jason, next screen, please. Okay, it's overall the strength 3 and strength 5, which is wind, they control the design. And for service, there was it was a modified service load case considered for this bridge, because imagine a bridge of this tall and the location that there was a possibility of high wind occurs with the temperature at the same time. Therefore, there was created a modified service load, which is a wind at 115 miles per hour, which is corresponding to 80 miles per hour base wind versus 50 miles per H2 or design manual for. And that also control some aspect of design. As I mentioned, that we did all these load cases and load combination for different stiffnesses based on using that moment curvature section properties. Next screen, please. For pier design, we use PA program. However, because from our stat, we computed the moment, because that moment is a function of that P delta. And we were not supposed to use the moment amplification factor in PAP. And then also because, you know, the moment was different based on the stiffness, we took the moment from the stat model and we manipulated some parameters in the PAP input to make sure that the design of the pier will be based on the shear and the moment of the stat model. Next one, please. These are some reinforcement for the stem. As I said, that we divided the stem in 28-foot segment, except that in a one odd segment at the bottom. This made it very easy for us for the drafting, a lot of saving in the drafting, and also a lot of saving for the contractor, that he knew that all his sections are, except that one section at the base, are going to be 28-foot long, and then his forms and everything reused over the entire 15 feet based on that 28-foot. Next one, please. Jason, next screen, please. The other thing that was a strut and tie method we used here, that in a strut and tie method, as per AASHTO, is our cap and our footing and our and the plinth at the bottom that were, you know, supposed to be do with a strut and tie method analysis and beside the conventional. We did a several strut and tie method for the cap and for the footing and for plinth, and then and based on those results, we revised our reinforcement, and it was the worst of the two traditional analysis and a strut and tie method, especially with the cap shear reinforcement controlled, you know, by strut and tie method. Here you see a model of a strut and tie for the cap. This is for the full width of the bridge. And also we did another one, which is next screen, that, you know, we did it for the half of width construction. Also, we analyze our pier cap for strut and tie method. This is the strut and tie method model for the half of width construction. As I said, that, you know, the shear reinforcement controlled by a strut and tie in this model. Next screen, please. This is the plinth I was talking about. That as you see that the plinth is in line with the stream, and then the stem is skewed to the plinth. This plinth, the plinth I mentioned, is approximately 60-foot long and 30-foot wide, and something 15 to 25-foot high is you know. And we did a strut and tie method for the plinth also. Next screen is this is the strut and tie model for the plinth, which is very sophisticated and complex trial and, you know, error method to find out your correct model for your strut and tie method here. Some of the reinforcement or their, you know, their length, you know, controlled by development length controlled by the strut and tie method, which will be adjusted accordingly. Next screen, please. This is the actual reinforcement of the plinth. You can see how massive it is. Next one, please. Okay, you know, it's again, this is described that, you know, before that, you know, abutment were on steel piles, and the piers were on, you know, the 9 piers, you know, on a spread footing, and the 5 piers on 5-foot diameter caisson. And we use L pile and SP column for design of the caissons. Next one, please. The design lesson we learned here is that, you know, the time we spent it on those substructure analysis, it paid off because we made a significant saving in the rebars. That the strut and tie method on all of those provided a much more accurate design. And also that the moment curvature was much, you know, it provided very accurate design, and it resulted in correct, you know, distribution of the load between the substructures. And also, as I mentioned before, that the service moment, the modified service moment, that control part of our design. This is, you know, the overall design and overview of our substructure design. Now Matt is going to talk about the construction topics.
Hey, good afternoon, everybody. Can you hear me?
Yes, we can.
Yeah, we can hear you, Matt.
Okay, just making sure an audio check there. So for the construction side of things here, one of our first challenges here was gaining access to the foundations for the bridge. If you can go to the next screen there, I can show a picture here. We had several types of shoring that was required. This picture here to the right was taken from abutment 1 looking out across the bridge. Of the 14 piers, only Pier 1 could be open cut, which is in the foreground of this photo. All of the land piers adjacent to the railroad tracks, which is on the other side of the river from this photo, they were all more or less a custom cofferdam to address each track individually. Then all the remaining cofferdams required for the land piers were of a circular cell with a concrete whaler. We somewhat standardized that process to help, with fabrication, material procurement, and then, construction in the field. And then there were piers in the river. All of those we standardized cofferdam frame and used sheet pile out in and around our causeway for access to those foundations. Next slide, please. Here is a snapshot of our circular cell design. So it's, as you can see in the photo there, the foundation, the footing of it is in the wide open. As large as these footings were and as deep as they were, range from 25 to 30 foot in depth approximately. A rectangular shaped cofferdam, most designs we looked into would have required some type of center strut, which would have conflicted with both the foundation formwork and the stem formwork. So a new approach was looked into where we actually did a circular cell. So yes, we fit a square peg in a round hole there. We just made the diameter of the cofferdam large enough to encompass everything. And we used a concrete whale to support the sheet piles we excavated our way down. On the next slide here, you'll see a few pictures related to it. So on the photo on the left there, we would drive our sheet pile in the circle. We had to design and construct a template. It was a chord section of that diameter that we could then set. It was 11 or 13 pair of sheets off of this template. We put onto it some survey markers so that way we could model it in a file and our survey could go out and shoot that template in so we could place it where it belonged. Place our sheets around, drive them deep enough to be secure. Then once we made closure of that circle, we drove them all to depth. The photo on the right here shows the concrete whale construction in progress. You see the first whale there is suspended in the air. There were rebar hangers that were welded to the sheet pile because it would prevent any kind of slippage or movement of that concrete whale during the time as you began excavating the cofferdam before the sheet pile, deflected with their load and engaged into that whale. There was concern that their movement could occur. So these hangers were used to eliminate that. Next slide, please. See here on the photo on the left, the controlling condition for these cofferdams was actually not the final condition where we began construction of the concrete footing. It was after the second concrete ring was constructed and while excavating for the third. Because in that condition, your cantilever of the bottom of your sheet spanning down below that second ring was at its greatest. Once the third ring was in place, the remaining excavation was removed to achieve grade for the bottom of the footing. You can see here in the photo on the right that this approach to a cofferdam that allowed us free rein access. We didn't have any center struts to phase in and out or to work around, and we were free to fly our formwork in and build our pier stems without any distractions. Next slide, please. So our river cofferdam, we employ a similar concept where we designed the cofferdam template to be large enough and we utilized a corner style bracing. That way we could eliminate any type of center struts here as well. And we would design this frame and it was used for all of the piers in the river. It had to be large enough to encompass the construction of our footings, but it's actually small enough so we could get a drill rig to reach from the top surface to drill all 8 of those caissons. And on the next slide here, we'll see some more information there. So in the photo on the left is that frame. We had it fabricated and assembled on site, and we would pick it up and set it in place as one pick. And we had 2 of these that we would leapfrog as we build our piers across the river. The photo on the right, in order to drill down in and around those caissons, there was not enough room around the caissons themselves to fit a drill rig. So trying to figure out how to perform that work, we decided to get to it from the top side, which is why we had to keep the sides of our cofferdam small enough to reduce the span that this platform would need to reach across. On the next slide here should be some design details. So the platform was never designed to actually support the drill rig to tram across it, but more so to creep over top of the sheet pile, as you can see there on the right, to gain access to the drill shaft. So we would put these in 4 positions. So you could drill 2 drilled shafts at a time. You would drill 1, the rig would then back up, tram around, and enter onto the platform from the other side, and then construct that shaft. And then we would move that platform along to each position to get all those shafts built in place. Next slide, please. Here's a few photos of that work in action. You can see we cased the open air space from the platform down to the rock surface. We did that, one, for safety concern for any people, as you can see down in the hole, they're not exposed to any kind of bit or debris in the open. It also protect the hole from any kind of fall inside. But lastly, it also kept our shaft clean. We would case into the rock a few feet, so that way when we would drill and clean out the shaft, we would not have any surface water or anything leaking in through coming in from the top. These drilled shafts, the cleanliness spec for PennDOT in this district was very strict and severe, and so that was a concern, and this helped a lot with that issue. Next slide. As far as pier stem construction went, we standardized our formwork. Each pier had a different height. So what we did is down low, while we were down in the cofferdam, we would do what we called a starter pour. That was the varying height. So that way from that construction joint on the first lift of the stem placement, from there on up to the pier cap was a standard height, 26 feet if I recall. So this way we did not have to reconfigure our formwork each time. Any of that reconfiguring was done down low on the ground, where it was easier to work on versus swinging up higher in the air. So then once that starter placement was constructed, we could then work our way up in standard units. That allowed us to pre-tie a lot of the rebar cages, as you can see there in the right-hand photo on the bottom right. We would tie those out ahead of time and stage them where the piers were at, and we would leapfrog our formwork accordingly based on the cure and the strength of the concrete prior to stripping forms. Next slide. Here is where I talk about the pier cap construction. A few different approaches were thought of, but ultimately we went with a shoring tower approach, where we called it a dance floor, where we would build the formwork, the floor of it, supported on top of shoring towers, and each tower had a foundation with, out on the causeway it was a spread footing, but on land we would drive a few H-pile to support that shoring tower. So then we would step that bottom portion in. We would get one of the walls erected up, and then in the photo on the right-hand side, you can see us going and setting the rebar cage that would be pre-tied on the ground, and set that up and into the formwork. And what we did is, because once you pour your concrete, you're going to lock in your loads onto that formwork. What we did to create relief, allowing us to strip those forms and get those shoring towers out, is we used a sand jack system that we came up with. We had a concern that any type of jacking system with the use of hydraulic fluid, should there be any leak or any hose or any kind of failure there, that could be problematic. So, we had a sand jack system, which was basically a box full of sand that had a plug on it that we would close. We'd fill it with sand that would put the shoes for those forms on top of those shoring towers where they needed to be. And then once construction was complete, we would take an air hose and put in that opening, and after we opened the hole and blow the sand out, which would create the relief, allowing us to strip the form. So that was a neat little trick there that worked out well. Next slide, please. For the steel erection, we subbed that out to Century Steel. They did not use shoring towers to erect the girders, with exception to around the railroad tracks, as that was a requirement for Norfolk Southern. So they would use multiple cranes in tandem. And the next slide here will have a picture of that. They would use the first two, if you want to go to the next slide, Jason, here on the photo on the left, they'd use the first two cranes to start setting the process, and then the third crane would come in and help, and they would leapfrog across the way, making field splices in the air. So the pros and cons here is it is a faster way to go. Con is once you start, you're committed to finish that span for that pair of girders. So we had to pay very careful attention to the wind. So, in the middle of the day, if we thought wind was going to pick up based on the weather predictions, we had several that we consulted throughout the day. We would have a go, no go decision to make sure that we were not partially way through erection and then get affected by wind and have any problems there. And that planning worked out well. We had no issues related to that during the erection of any girders. The photo on the right shows where the first phase was complete. The river, we can only build the causeway halfway across at a time. So we could build one unit fully on land and a portion of unit 2, which was the unit that spanned the river. And this photo on the right here shows all 8 of those girder lines. I thought that was neat to show. Next slide, please. Here's just more photos of the steel erection. We had, in addition to going across the river, we also had a live traffic we had to set girder over. We were allowed a nighttime detour, just one night at a time, to set the girders. So we had traffic set up during the day where we had barrier to take some shoulder width where we could deliver and dress the girders to prep them for erection the following night. And the photo on the right shows some of the shoring towers that were required for erection in and around the Norfolk Southern Railroads, the tracks. Next slide, Jason. Here's a nice picture on the left, just for scale, of what it looks like when you were walking on the deck with that mile of rebar. So the photo on the right has a nice picture of the 3 phases of the bridge. You can see towards the left where the bridge is more or less complete and the concrete deck is complete, but then portions over the river were following suit with deck rebar, and then unit 3 there to the right with steel erection. Now you'll notice in this photo, the causeway is now on the right side of the river. We could not, like I said, build the causeway across the entire river. There were flooding concerns there, ENS restrictions. So we would build the substructure and set the steel girders, and then all remaining construction of the deck and parapets would take place without a causeway under you for that portion of the bridge there. And some major challenges were, how do we physically get material out onto that deck? And for the most part, laborers had to carry it. You can see here on this photo another picture of the staging where we do have a causeway. We could use a crane to set it, set the rebar up on the deck. Now, another challenge we had here was a slick line. In order to place the concrete out into the river sections, we had to develop an alternate triple AP mix and concurrent with PennDOT to meet their specifications. So we could come up with a mix that would perform through as much as our longest slick line placement was through 1,500 feet of slick line, which is a challenge. Next slide. Here is just that mix design, if anybody wants to look at that later. You go to the next slide there, Jason. One of the last things here before questions is with our overhang jack design, it was pretty straightforward, but one challenge we encountered with is up at that elevation, with no trees, no anything around, and it wasn't a high wind location. We encountered problems with overhang jacks being flipped up by the wind. So we developed a tie down system that had a slack line in it that would only let the overhang jack move maybe a quarter of an inch, and that slackness was required and important, so it didn't add any more downforce to the overhang jack and potentially overload it. Because we did use our overhang jacks to carry the weight of our big well system in lieu of placing anything over top of it. And with that, any questions? We can turn it over to the other presenters.
So people can feel free to put questions in the chat or even unmute and ask questions of the presenters too. So I guess, Matt, I had a question. How long did one of the circular cofferdams take to construct?
Did you catch that question, Matt?
No, I didn't. There was something echoing there. Could you repeat?
Yeah, my question was, how long did one of the circular cofferdams take to construct?
All in, probably took approximately a month and a half to drive the sheets, excavate down, and form and place each concrete ring. We had to achieve a certain strength, and strain gauges were placed inside each ring, and that would dictate when we could begin excavating again. So I would say about a 6-week process.
Okay, thank you. All right, so we have a question in the chat here from Greg Dunn. So great presentation, a few questions. Was there difficulty sourcing the 3 1/4 inch plate? That's the first question.
At that time, no. We would have procured that material sometime in 2016. Should we be doing the same thing today? We would likely have some troubles there. But at that time, no. That was not really much of an issue. More problem we had was procuring the sheet pile.
Okay. All right, second question from Greg. What caused the discrepancy in stiffnesses in Unit 1 where 50% of the load went to Pier 1 and the remaining 50% distribution to the other 3 piers, 2, 3, and 4?
Well, as I mentioned, that was because of the stiffness of it. That pier was a shorter pier, and then stiffness of it, because a lot of moment and also displacement at that end. And what we found out in our model that, the forces, the wind, applied to the substructure of, let's say, Pier 3 or 2, went up through the bearing into the superstructure and went back to the Pier 1. Which, this is something normally we don't consider, that how wind to the substructure goes through the bearing back to the other substructure, which the model showed that happened.
Okay. And then lastly, how did the modified Service 1 load case with 115 miles per hour come about?
As I said, that was because of the, to be a little bit conservative and realistic, that, that's, we said that the possibility of the wind of this amount with the temperature, high temperature day could happen, that structure. And I think that was, the decision was made originally by the district, and it was a good decision because just the probability of such a thing could happen.
Okay. So we'll hold on for a minute or two here, see if any more questions come in.
Yeah, one comment about the wind in the meantime is we did have wind meters on our tips of our booms, and we've experienced winds during construction. We were not working at those times, but in excess of 85 miles per hour. So there may have been even higher than that at times we were not recording. Just to validate, I'm out there with 115 miles per hour.
Yeah, that's good to know. Okay, well, I haven't seen any other questions come in. Overall, I wanted to thank the three of you guys for presenting today. It was a great presentation, instructive on the design side of stuff, on the design side of things, as well as on the construction side of things. So thank you again. This is our outro slide here, so upcoming events. We have no presentations for the remainder of the year, so have a good summer to everyone. And tomorrow we have our SEI golf outing that helps support the SEI scholarship to students in the Philadelphia area. So thank you guys. Thank you for joining. And thank you again to the presenters.
Thanks, Jeff.
Thank you, Jack.